So what are we going to present today? So we're going to present this paper, which is entitled an expressive and modular layer activation mechanism for context-oriented programming. All of those terms are going to become clear in a second. This paper was presented a couple of weeks ago by Paul Leher at ICSB. The paper is coming from a journal publication from earlier this year in the Journal of Information and Software Technology that was published in April this year, right? I have to give props to Paul because he was the one that made these slides, and so all the credit comes to him. And that's it. So this is work on the line of context-oriented programming, which was made in conjunction with Paul, that works at Universidad Católica in Chile, Universidad Católica North in Chile, and Hideki Masuhara, that works at Tokyo Tech in Japan. Okay. So what are we going to talk about? Well, a modular and efficient scoping mechanism for context-oriented programming. So I'm going to go about a little bit everything that those terms mean, explaining mainly what the idea and the problems that we found in context-oriented programming development were, and that were the motivation for this paper. And then we're going to go through the full explanation of what we did and the validation of the paper, right? So let's talk first context-oriented programming. The idea of context-oriented programming is that more often than not, you find yourself in a situation in which for a single application, you see that you need to implement behavior in two different ways. Yeah? So this is a simplified example, and it's like a larger version of the common context-oriented programming example of moving your phone from landscape to portrait and observing a different behavior when you do that move, right? So for example, here, when you see the portrait mode of the phone, then the controls look completely different than when you have your phone in landscape mode, right? The controls for the game. And it's exactly the same application, right? So how would you do this? Well, there are a couple of ways of doing it, but the main idea in which you can do this is that eventually you will have to define a pool of methods that define this behavior for all these different situations, and you will need to manage them somehow. And this is problematic for a couple of reasons, but the main problem with this is the maintainability of this approach. And part of the problem is that whenever you have multiple implementations, like in this case, adding a new implementation will be problematic. You will have to go into the code and make sure that the new implementation does not collide with any of the other implementations, and you will have to manage that. There are architectural solutions for that, but then you will have to define the architecture that you will still need to modify. So this is problematic, and it's mainly a maintainability, reusability problem. So the idea of context-oriented programming is that context-oriented programming is a programming parallel approach to deal exactly with this situation. So the idea is that context-oriented programming proposes a way of building programming languages that let you adapt dynamically the behavior of an applied application without jumping into this maintainability problem, right? So that is where we're going. How does that work? Well, whenever you have different ways of executing your application, which in context-oriented programming we call contexts, these are identifiable situations that you see that make the behavior of the application change. That is the main idea of this. And then you can define specific behavior for those, which means that in your program, you need to have two different entities, which are abstractions in context-oriented programming. So the first thing that you need to define is the concept of layers or context in context-oriented programming, depending on the flavor of language that you are using. But it's a new model that you define in which you say these different situations are going to be relevant for the execution of my application, right? And then within those contexts or associated to those contexts, what you do is that you define the new behavior that you want to observe, right? So you define your basic application where you are just saying, okay, this is my application, this is the behavior of my application, But whenever something different happens and I need to observe new behavior than what I implemented, so for example, here moving the phone from portrait mode to landscape mode, then I'm going to do something different, right? And what you're going to do is that you're going to re-implement this specific method here in a different way. The key of this is that that new implementation is going to look exactly the same as the previous implementation in terms of the signature of the function that you're implementing, right? So there is no difference there. You don't need to add like a difficult structure around the around your objects. You don't need to worry about polymorphism or things like that. You don't need to worry about adding new variables, parameters to the methods to know like in which mode you are executing. You just define exactly the same method with the same signature, give it a new behavior, like a new function implementation, and that will work for whenever you jump into the landscape mode. So the idea is that when that happens, you will not execute for the player view this draw method, but you will execute this new draw method that you just implemented. And the point of having like this line here is like you're making those two entities completely independent. So you don't need to be aware of anything about the implementation of the original code. You just need to know which functions you want to change, like the signature of those functions, and just implement them as new modules in the application. So that is the main idea of this, with a missing part, which is being able to see that behavior, right? So to make all that work, because so far in the left-hand side of the slide, we just define the new behavior and the context or the layer associated to that new behavior. Now we need to make it work. And the idea to make it work is that we need to be able to detect whenever a particular context is present in the execution environment of the application, right? So in this specific case, we need to know that in the phone is portrait mode, we need to see whenever that change to landscape mode happens, and that will trigger what we call an activation of the context. So that action will tell the context landscape in this case. We are in a situation in which this context is relevant, and now we dynamically and automatically, like you don't have to worry about this process anymore, just simply change to the implementation over there. And whenever you change back your phone from landscape mode to portrait mode, the same will happen. You will say, okay, we are no longer in landscape mode, so that landscape context should not apply anymore, and you deactivate the layer, right? And what happens there is that you revert back to the original behavior, which will be the original implementation of draw that is there in the base method. Right? So that is how context-oriented programming works. So the key of this work is on the activation mechanism, right? So that is part of the, well, that is the key of the work, that we are going to modify that activation mechanism and to be able to make it more modular and to change the scoping of the layers, right? So how do you activate a context? In this specific work, we use a way of doing it, which is an implicit activation, which simply says whenever you detect a particular situation, like the screen angle of the phone, like it's over a 45-degree angle, so you're tipping it from portrait to landscape, then you just simply trigger the activation of that landscape layer, right? And that's the way we're going to use it. We are going to see in a bit other ways of activating a particular context, but this is the one that is implemented in our solution. So that is the important note there. And yeah, we'll move on. So that is context-oriented programming. We are focusing on selecting context, which is this activation of how do you decide that a context is active. And here the key of this is this expression here, that you need to be able to go into the base code of the application and say, I need a base code variable that tells me what is the situation that I have, right? And the other part is what happens when you actually activate a layer, right? So you have your base code, you activate a layer, and so far what we have said is that the new behavior that you implemented in the layer is just going to be part of the code, the observable behavior that you're going to see, but that does not need to be the case, right? And there are different situations in which you don't want to do that, right? So let's look at those two points specifically, right? So the first thing that we want to see is the association between the activation of the context and the actual context, right? So to be able to activate a context implicitly, explicitly, through event-based mechanisms, like all the ways that you can do it, is that somehow you need to retrieve information from the base behavior of the application, right? So this specific behavior here, like Espinano, is going to need information from the behavior of the application. It's going to need to know the value of that angle variable that is defined within the application, right? And it's the same if you use external sensors, like you need to go and fetch that information that lives there, and that is basically program information, right? Which doesn't seem like a problem on its own, but as we're going to see in a couple of slides, it has a problem, right? And it actually has a couple of problems, which is what happens when you think about reusability of the application and then on the evolution of the application. And here the application means everything that we are going to see situation, what happens in both sides of the application, right? So let's talk about reuse. When you want to reuse the application, then nothing weird is happening. So you define your application, you define your layer that is somewhat related to the application. So this creates a coupling between the layer and the base behavior, right? Because you have this variable that you need to use from the layer, right? So what happens if you want to deploy this layer in another scenario, right? So now you're not using a phone, you're using a new tablet, a different type of tablet that all of a sudden uses that concept of the angle in a different form, right? So then you will have a mismatch because this condition that you have here doesn't make sense anymore, right? So if here you're using degrees, like as a simplification of an example, here you're using degrees, there you're using radians, and then the angle that you're reading, the information that you're getting out of the application is going to be different, and one of two is not going to make sense, right? So you need to do something about it, right? And the main problem here is exactly that you have that, well, the dotted line here between the layer and the different points of the application where you can get that information, right? So that is one part of the front, but what if that table doesn't have a concept? The tablet there doesn't have a concept of an angle, right? So what can you do? Maybe because the concept doesn't exist altogether, and then you'll need to get it from another source, or because that concept is just defined differently in the application. So it's not called an angle, but it's called the inclination of the tablet, right? So there is a problem because here you need the angle to be able to use that layer. So whenever you want to jump into the tablet, then this layer is completely unusable. You will never see the behavior of the layer, even if you are actually using the tablet in landscape mode, right? So reusing, it's a problem. And the problem with evolution is actually quite similar. So if you all of a sudden change the version of your application from using a specific angle to using another type of angle, so when here you divided the general concept of the angle into two different types of angles, and so like the planar angle and then the elevation, and because that makes sense for the application, then the same thing is going to happen to your layer, right? So you will need to change the layer to be able to correspond with that behavior and the new angle that you're defining in the behavior. So both parts of the applications that are supposed to be independent actually are not. Because when one changes, the other will have to inevitably change, right? So not ideal, right? So that is the problem with the selection of the adaptations. So figuring out when an adaptation is active, when a layer is active, right? And then the other part is the scoping mechanisms that you're going to use, right? So for one specific game, as we're running with this example in the slides, and one specific game is perfectly fine with using that angle. It makes sense for that sense. It makes sense for that game, and it's actually going to change everything that relates to a draw method, right? So maybe here you have in the player view a draw method, and if in the screen you have another draw method, then it's going to change all of them. And you could think about that makes sense for other games, right? So you could do exactly the same for these two games, just define that landscape layer that tells you how to draw the application when you are in landscape mode. But maybe the behavior of the game does not make sense for all the games, right? So in some games, you may not want to actually change the way in which the game is displayed, right? Just the way in which the controls are displayed, which are two different entities, but because you're drawing the full screen of the application with that layer, then you're going to run into a problem that you can use this specific layer. So this is the particular example. So you don't really want to change the orientation in which you display the things. For example, in Tetris, because everything will need to, like the dimensions of the game will need to change. That doesn't make sense. So you would like to keep the game in exactly the same situation while changing the controls, right? And that's exactly the problem with scoping, because you don't want to change everything that you can draw. You just want to change some things that you can draw, right? And that's the scope or the effect that you will see from the layer in your application, right? So those are the two problems that we want to solve, and the way we solved it was to propose a small extension to context-oriented programming with a new language that is called EMA. So EMA is the general language, and we will see later an implementation of EMA, a specific implementation of EMA in JavaScript. But let's see what the solution of EMA is for those problems, right? So basically, we just defined two different ways of managing, well, both the scoping of the application and the selection of the scoping of the adaptations and the selection of the adaptations. So the first idea to be able to separate to be able to define the selection of the application, we actually divide the base layer of the base level of the application with the context level of the application, right? So those two models that we wanted to make independent, we actually are making them independent. The way to do that is by introducing interfaces which make a divide between what you define in the base layer and what you define for your layers, which is a proven solution. So this has happened before in the history of computer science. And whenever you need more modularity and to lower the code of your application, then using interfaces is a solution that works, right? So that is the first thing that we want to do. So for each of the variables that we want to use in the context-oriented level of the application, so in the new models, we just be able to, for the definition of layers, then we define this interface that is going to work as a bridge between the base level and the context level, right? And so this new little square here, that is the one that is defining the interface, right? So you are not going to use the angle of the screen directly, but you're going to use the interface that screen is exposed, right? Which is this rotation name here, right? It sounds silly, but we'll see a solution, right? So that is the first thing. And the second thing that we implemented was a way of basically defining how do you want to scope each of your layers whenever they are going to be used, which is this solution here at the top of that part of the screen. So we can have different strategies to scope the layers so that in some situations, the effect of the layer is going to be in a set of objects, and in some situations, the effect of that same layer can be seen in a different set of objects, right? So going back to the problem of that we had with Tetris. So now, for example, in Tetris, we want to be able to use this layer just for the controls and not for the full game, right? And that will leave the behavior of the game untouched. So that is the basic idea of what we want to do, to be able to reuse the code. Then what we're going to use is define that interface. That interface just acts like as a bridge between the base level and the layers. If you want to use that interface in another application, so going back to the tablet, then you can just implement behavior on top of the interface to keep the interface the same. So we have rotation for the smartphone and rotation for the tablet, which are the interface which is the interface that we're using, and what the rotation means for each of those is different. So going back to the example from earlier, if you in the screen you're using degrees, then you just keep it straight, so it's the value that passes exactly the same. While if in the tablet you're using radians, then you use the formula to change from one to the other, right? So you're changing to degrees, and then the layer is just talking to this new concept of rotation, right? It's just having contact with the interface, which means that now all the codes from the smartphone and all the codes from the tablet are completely dependent, right? So we effectively were able to modularize the full application with just the introduction of interface, right? What happens with the evolution is something different. Is something similar. Sorry. So whenever you jump from using the angle in the screen here and changing it to, let's call it again the planar angle and the inclination, yeah. Then you just change the definition of that part in the interface. The interface keeps exactly the same for the layer, so you are not actually changing the behavior of. You don't have to touch the code of this part of the application. You just touch the code in this part of the application because it's the one that is evolving. The same thing can happen on the other side. So if you want to change the way in which you define when the landscape mode is on, you can do it, and that is not going to have any effect on the base code of the application, right? So again, we made them completely independent in there, and the same thing will happen with the when you're reusing these interfaces. So one may change and the other keeps exactly the same, and then there is no problem for the layer because you're actually using the interface and not the specific value of the application. So the evolution of the application now is completely independent, and things don't have to co-evolve, right? So that is the first problem that we wanted to solve, and our solution is using interfaces. Then the second problem is using the scoping mechanism of the application. So these are three of the most used ways of defining the scope of an application. So the imperative scope is based on the lexical scope of the definition of a layer. So here we're using in the first example, in the imperative example, we're using the width landscape construct that applies the layer to all the code that is defined within that block. So this player view.draw function is going to be used use the draw definition of the landscape method because it's there. And it's just an imperative definition. And then the event base works similarly. So whenever you see an event, then you actually activate or use that specific layer. And the implicit mechanism is the one that we're using. When the event happens, just automatically you activate that layer, right? So that is exactly what we want to do. And the way in which we want to use it is to be able to implicitly define a specific scoping for the application, which is exactly this way. So whenever you want to use all those games that are all the way to the right, then you just use a global scoping saying, if I'm in landscape mode, my new draw definition, the one that is defined in the layer, is going to affect all the draw methods that are defined in the base level of the application. Well, if I'm playing Tetris, I'm just going to define this strategy for a specific object. So I can go into the controls of the application and say, you know what? For this specific control, I'm going to use the definition of the draw method that is defined in the layer. All the other draw methods are going to keep exactly the same, right? So you can affect that, and there are other ways in which you can do it, like the details of all the definition of the scoping mechanism are in the paper. So that's exactly what you want to do. And so we still want to use an implicit activation mechanism. Actually, in EMA, we are using a reactive mechanism. The variables used for the interface are reactive variables, just that it's easier to get the information there. So that is there. And then the scoping mechanisms we define whenever we trigger the activation of the layer, right? So you see the condition of when a layer should be active, and whenever that is, becomes true, so it's a predicate. Whenever that becomes true, then it triggers the activation of the layer. Here are just three examples of the way in which you can activate the layer. So one thing that we added was the sense of what kind of effect is going to be is going to have the layer on the object. So here this all of means that we are going to apply the layer for all the objects that meet this condition, which is exactly the predicate that we had defined before. And we can also expose that to a specific object. So this is what we usually call a local activation. So we are activating this specific behavior associated with the layer for one local object. You can define it for a specific thread or for a specific block in your code. That is the same. And just to make it different with scoping, or so this is for a specific object instance, this screen object instance, that one. And then in the last example, we have an activation where we're saying we just want to activate for one of the objects, if there is any of the objects that satisfy this condition, just for one of them, we want to activate the layer associated with this condition. And what kind of object are we going to do it for this specific object? So any object that satisfies being of type string, then one of them, from all of those, one of them is going to get activated, right? And you can change this for different behaviors. So if you want to activate a couple of contexts, if you want to uniquely activate a context so that the context becomes active and all the other becomes inactive. So those are the kind of situations. Again, the details of like all of the semantics of the scoping mechanisms are in the paper, but this is just to give you a hint of the solution that we're proposing here, right? And that's pretty much solves the second problem. So now we can have like a flexible activation mechanism, because we can define when to activate a context independently of whatever the base behavior is, and we can define what the effect of that context is going to be independent of what the base behavior, right? So we can define it specifically for what we want for one particular context. And we may want to use a global approach so that all objects are affected by that context. And for exactly that same context, we may want to say, no, for in this specific situation, I just want to use one specific object instance, right? So being able to do it like that. So how does this work? So to make all of those ideas work, we implemented EMA as a super language of JavaScript. So it's JavaScript all the way down with the new abstraction. So you can develop JavaScript normally, so define objects in JavaScript without any problem. Then you can define layers. So we have this abstraction of layer that you can define, and then layers are associated to a specific condition. So that condition uses the interface that we want to use, so rotation in our examples. Then for that, we want to push forward the actual interface of the base code into the system so that the layer can read that. which is doing exactly what we described previously. So this the angle variable for the screen now is going to be exposed as this new interface for rotation into the system so that the layer that we just defined can use that rotation element, right? And the last part of this is to associate all of these concepts together, right? So we have the layer, we have the objects that we, like the system that we want to adapt, we have the layer, the system object that we want to adapt, and the specific new implementation of the system, like that new part of behavior that we're implementing into the system, so that whenever we jump into the landscape mode, then objects of type layer view are going to be changed in the raw method by this new behavior that we're implementing, right? So that brings it all together in the language. To this, we implemented like a domotica example, so a smartphone scenario, and just a simple scenario where you get to a house, and then when you ring the bell, what should happen? Well, that alert that of the bell ringing should be propagated to different devices in the house. So here we're just making it ring in all of the devices that are connected to the house. But actually, that may not be all the behavior that you want to see all the time. So one particular situation that is implemented is that you just want to have this event being announced, advertised in the rooms where you have users in the house. So, for example, here in the living room, is the only room in the house where you have a user. So you will only see the alert in this specific room with all the devices. There are other situations that we take into account in the paper to be able to demonstrate how to work with the different activation mechanisms, the different scoping mechanisms, right? But that is pretty much the idea. And what is the result of this? The result of this is that we compare the implementation of this study between using regular object-oriented techniques to implement this type of behavior. So basically using design patterns to be able to have these different implementations of the behavior using regular context-oriented programming languages and using EMA. And what we saw as we were going down through the implementations is that the new abstractions that the languages are presenting generate a program that is more concise, which is good because there are less opportunities for bugs. But another thing is that with EMA in comparison to the other two specifically, is that we see an increase in the modularity of the different concepts of the application. So what you see here is that you can actually focus on developing the behavior of your application and then leave all the contrived mechanisms in which new behavior is introduced dynamically into the application, to the language, and in the way in which you manage that behavior, which would be the last part for all the behavior defined associated to the actual adaptations. Then that is also concrete to the new behavior that you're defining, and then to managing all those adaptations, you widely reduce the time that you have to spend there during the implementation, right? So this is just a small example. The validation in the paper is obviously larger with another case study, in which we demonstrate how exactly how EMA works and how is successful in satisfying these requirements on increasing the flexibility of the selection and scoping mechanisms in context-oriented programs. So we just have this implementation, but we also looked into all other context-oriented programming languages that are out there. And so since 2005, where the first language of this type was proposed through pretty much the publication of the paper, we went through all of these papers looking exactly at what is happening with these two aspects of the language, so the selection mechanism and the scoping mechanism. And most of them present opportunities to be able to work with the two concepts, but the semantics are fixed, right? So activating a context and scoping that specific context, they have fixed semantics most of the time. So you can only activate in one way, and then you will jump into all these reusability and evolutions programs that we discussed. And then the scoping is usually one way or another. Sometimes you can do it for different layers, so different layers can have different scopes, but the same layer is not able to have different scopes, right? So you're still constrained there. And so this is the first actual work that implements this concept of interfaces, reaching a truly modular implementation of context-oriented programming and these adaptations ideas. And it's the only one that has a customizable scoping mechanisms for the applications. So that leads to conclusions, which is the main 2 points driving the situation. So EMA is actually expressive enough to be able to have a truly modular implementation of your language, of your adaptations, that is based on context-oriented programming, and it's an improvement on the modularity of existing context-oriented programming proposals. And not a smaller fact, EMA is actually working. You can download the implementation there. There is the full implementation with the implementation of the 2 case studies that are part of the paper. And of course, you can see the paper there.